Alrighty, folks, welcome to calculus. So in this video, again, I apologize that I have to be your teacher, but we have explored some of trig integration in the last video, in our last lesson, 8.3. But the next one that we're going to get into is we are going to actually use trigonometry or trigonometric equations to substitute into our function or into our integral to make the integration much easier. So that seems like it would be making it more difficult, but hopefully you'll see and you'll kind of catch on to the tricks as to how it becomes easier. So the main things that we're going to be using are sine squared plus cosine squared is 1, and the fact that tangent squared plus 1 is secant squared. Those are the two identities that they kind of stick to. Beyond that, I don't really see them do the cotangent squared plus 1 is cosecant squared. But there's no reason why we couldn't do that, I wouldn't think. I think that's just more annoying is all it is. But these are the ones that I'll see more often. And with this section 2, do know that this is not going to show up on your AP test unless they tell you like specifically to use a specific trig substitution. But this idea of having to come up with it out of thin air isn't going to appear on the AP test. That is something that you will see, or at least that your college professors will expect you to know when you go into Cal 3. So all of the BC teachers around the United States also teach this, so you guys get to learn it as well. Okay, so looking at this first one, right, it kind of looks like it should be arcsecant or something like that, but it's really not, right? Because arcsecant would have been x squared minus 16, and this would have just been an x, and that's not arcsecant, so that's not an identity that we know. We cannot use U substitution. That will not work either. So when I look at this, what I notice is that it is a number minus an x squared. So the way this is going to work is I'm going to specify exactly what I want x to be. In this case, since it is a number minus an x squared, I am going to rewrite this identity such that cosine squared equals 1 minus sine squared. And the reason I'm showing you that is because I am going to say, well, I feel like letting x be 4 sine of theta. Now, why the heck would I do that? Well, I'm going to make that substitution for x, and notice that my terms of integration are also in terms of x, my dx there. So I do need to take the derivative of my x and make this 4 cosine of theta d theta, such that when I make my substitution, now my integrand will all be in terms of theta. So let's go ahead and rewrite this and just see how it works out with algebra. So this is the integrand of 1 over 4 sine theta squared, square root of 16 minus, right, 4 sine theta squared, so 16 sine squared theta, and then times my dx, right, because I have to make the substitution for dx is this junk, so times 4 cosine theta d theta. All right. So now this has a lot more stuff that I can mess with, because I'm going to go ahead and factor out the 1/16 with this part here, right, because that's 4 squared. So I'm going to bring that 1/16 out, and this is the integral of 4 cosine. I'm just going to leave the 4 cosine for now, over sine squared theta times the square root of, if I factor 16 here, this can be 1 minus sine squared, and then I have a d theta. So now the nice thing about this is that 1 minus sine squared, right, which is what we set off to the side, is cosine squared. So what that allows me to do is I can rewrite 1 minus sine squared as cosine squared such that I can actually take the square root of that thing. So let's go ahead and do all of that. And please remember, as you guys are going through this, with these lesson videos, I intend for you to kind of pause the video to write, understand what I'm talking about, try to make sense of the steps for yourself. Write down your questions, email me questions. That is my intent with these videos. I know I move kind of quick and you're probably like, well, slow down. Use technology to your advantage, please. Alrighty. So I'm going to make the substitution. I'm actually just going to duplicate. Alright. And that 1 minus sine squared is now a cosine squared. And the reason that is nice, I'm going to leave the 1/16 on the outside still, is that I have 4 cosine theta over sine squared theta. And then the square root of 16 cosine squared is 4 cosine d theta. And then check that out. I have some terms that divide out, my 4 cosine. So I am left with 1/16 integral of 1 over sine squared, which 1 over sine squared is cosecant squared, d theta, which the antiderivative of cosecant squared is negative cotangent. So this is negative 1/16 cotangent, that's a cotangent of theta plus c. Cool, I got the answer, right? Yeah, I mean I did, right? We did all that and we came out with something that I could do the antiderivative of, but everything in the beginning was in terms of x, and I just changed it and I was like, well, here's theta, this is the relationship, you figure it out. Well, that's not quite the way it works. It would be nice, I wish. I do done wish. So we need to replace this theta and make it in terms of x. Well, a relationship between x and theta is defined that x equals 4 sine of theta. So going back to good old pre-cal days, if I say, well, hey, then that means sine is x over 4, and I know sine is the ratio of the opposite length to the hypotenuse. So from this angle, I should be able to say that the opposite is x, the hypotenuse is 4. So this missing side down here should be the square root of 4 squared minus x squared. So 16 minus x squared. Well, that's interesting that it ends up as that. All right, so what that means for me is now I need to rewrite this as negative 1/16 cotangent is adjacent over opposite. So root 16 minus x squared over the opposite side, which is x, plus c. That is going to be our final answer here. This is what they are going to be looking for. So I've rewritten everything in terms of x such that it is the antiderivative of my original. So really all that trig substitution does is it allows us to rewrite this in a more simple way and do it a more simple antiderivative. So please do note a couple things. One, it was in the form of a number minus a variable squared. So I related it to this. I chose it to be sine. If it were a number plus a variable squared, I would probably want my x to be a tangent. If it were a variable squared minus 1, I would want it to be a secant. I think we'll see each of these forms as we're going through the notes as well. The other thing to make note is the thing under the square root. Often this is useful with radicals. Not always, not forever, but often it is. The thing under the square root, I wanted to be able to factor it out of both terms. So I had to choose an x with the number such that when I squared it, it was the same as this number. So those are the kind of things that I'm thinking about. I think we have 4 more examples to roll through, so let's do this. Okay, so notice we have another radical, and then this one I have the variable squared minus the number. So I'm going to be thinking of secant. So if I make x 5 secant, please do feel free to pause the video, try the problems on your own. That's always a good idea. Try to think about, okay, I see how we got 5 secant, so maybe I should try the rest on my own. Try it. I'm going to work through it. I'm not going to stop. So please pause the video. Use this to your advantage. So 5 secant theta, tangent theta, d theta. So my integrand, I'm going to go ahead and factor out the 25. and then it'll be secant squared minus 1 over 5 secant, and then times 5 secant tangent d theta. This step right here, please do not forget to rewrite your dx. This is what I'm guessing that you'll probably mess up on if you mess up. So just be careful. Make sure you got all the parts in there. You're rewriting everything in terms of tangent, or sorry, in terms of theta. All right, so now I will have integrand of 5 tangent theta, right? Because secant squared minus 1, this should be tangent. Let's go back to our original identities, right? I can rewrite this one as tangent squared theta is secant squared theta minus 1. All right, so these are the basis of all of this, using those Pythagorean identities that you learned in pre-cal. All right, 5 tangent theta over 5 secant theta times 5 secant theta tangent theta d theta. Looking at this, I can divide out my 5 secants. There's no reason I had to do that other 5. I could have done this one as well. Just I did it with the 5 secant. So what I have left, I'm going to factor out the 5. So this becomes 5 the integrand of tangent squared, which I do not know tangent squared, but this is going to seem weird. I actually need to rewrite tangent squared as secant squared minus 1 to be able to do this antiderivative. Because the antiderivative of secant squared is just tangent, and then minus 1 will be minus theta. So I have 5 integrand of, 5 times tangent theta minus theta. I have a plus c as well. So now I have to do tangent theta, and I also have to do theta, but that's not going to be as difficult as it seems. I'm going to go ahead and draw my triangle. So I have theta, and then secant is hypotenuse over adjacent. So x over 5 is how that would work out. And then once again, notice x squared minus 25 was in my original I think that's pretty much going to work out every time that it'll show up somewhere. It's just the way the square roots work. They show up again in a second. So 5 tangent is opposite over adjacent, so root x squared minus 25 over adjacent is 5 minus theta. Now, I have a relationship between theta and x, and that relationship is that x equals 5 secant theta. So the way that I'm going to rewrite this and say that, hey, what that means for me then is that x over 5 equals secant theta. So then arcsecant of x over 5, right, secant inverse, must be my theta. And that's all they're going to be looking for. There's no reason why I couldn't say arc cosine of 5 over x, or arc sine of x squared minus 25 over x. There's no reason I can't do the other trig functions, but normally you will see this with the original trig substitution that was made. It's just how they'll write their answers. But there shouldn't be any reason why I can't do any of the others. So I have minus arcsecant of, what do we say, x over 5 plus c. You can distribute your 5 if you want to, right? So x squared minus 25 minus 5 arcsecant of x over 5. You're more than welcome to do that, but I mean, it's really whatever. You don't have to. Okay, that's all I can think of for this one. Okay. So I have a 9x cubed, 1 plus x squared. Especially when I have these, the first thing I still think of, I still go to like direct use substitution, or I go to like arctangent, or anything easier that I can do. All right, so I'm showing you a bunch of examples that have this special case where I can use the trig substitution. But please remember, all of your other integration rules still apply. If I can do straight use substitution, do it. If it's just arcsine, it's cool. It's just arcsine, do it. If I know the antiderivative, then just do it. This is kind of like just special case. I'm just trying to give you guys more tools. Okay, so in this case, I don't see anything else. So I'm going to let x be, it is 1 plus a variable squared. So I'm just going to let it be tangent of theta, such that I have 1 plus tangent squared, and I'll be able to turn that into secant squared. So then my dx actually is secant squared, theta d theta. I'm going to factor out that 9 while I'm rewriting everything too. So 9 integral of tangent cubed over 1 plus tangent squared. So secant of theta, and then times my secant squared, theta d theta. All right, so again, this secant down here, you're like, whoa, okay. So this is 1 plus tangent squared. 1 plus tangent squared is secant squared, so the square root of secant squared would just be secant. All right, now we can simplify stuff. So I have secant, I can divide out one of those. So I have tangent cubed times secant. Okay, hang on, my baby boy's crying. He's not feeling very well. Okay, he's all right-ish. All right, so let's see. From this point, right, we simplified as far as we can. This takes me back to our last lesson, where maybe, just maybe, I want to rewrite one of those tangent squareds as a secant squared minus 1. Because then I recognize if I make u secant, then du will be secant tangent. So this is a u substitution within this, so let u be secant of theta, or I don't know what I just wrote. So du would be secant theta tangent theta, d theta. So I have 9 integral of u squared minus 1 du, right? And again, that's because if u is secant, right, there's my u, so u squared minus 1. And then du is secant tangent, so tangent times secant theta d theta. So that is my du. Now I can do the antiderivative pretty easily. So I have 9 u cubed over 3 minus u plus c. But u is really secant theta. So I have 9. Well, let's go ahead and distribute that 9 just to make less fraction writing. So 3 secant cubed theta minus 9 secant theta plus c. But theta is not my answer either because it is in terms of x in my original. So I need to think about what triangle this came from. Well, it came from tangent is opposite over adjacent. So hey-oh, here is my 1 plus x squared side, square root of that by Pythagorean theorem. So secant will be hypotenuse over adjacent, so it'll be the square root of 1 plus x squared over 1. So I have 3 square root of 1 plus x squared cubed minus 9 square root 1 plus x squared plus c. You can leave it like that. You could also factor out a 3. 3 even square root 1 plus x squared, right? And then this becomes the square root of 1 plus x squared squared minus 3 plus c, which I could even write as 3 root 1 plus x squared 1 plus x squared minus 3 plus c. So 3 root 1 plus x squared and x squared minus 2 plus c. So I could write that from the very beginning of all of that junk. Beautiful, right? Wonderful. Okay, but really just last part, right, I would just leave my answer like this. I'm just trying to show you different ways they could rewrite this on a multiple choice question. Again, this is not on the AP test, but it will be on our quizzes and our tests because you will see it in Cal 3. Okay, I messed up. I have to do it again. Rather than just like teach you a wrong way to do a problem, I'll try to do it right the first time / the second time. Okay, so no identities, nothing here. I see that I can factor out a 2, so I'll do that. But the thing that's weird here that I missed the first time is that this x squared is being multiplied by 9. So in order to make this something that factors nicely that I can factor, I need to make this into a like x squared plus 1 such that I can rewrite it kind of deal. And since I have an x squared plus 1, I do need to think about tangent. But the way this is going to work on this one is that I want to make x 1/3 of tangent theta, such that when I do x squared, this will be 1/9 tangent squared. So this 9 will divide out, and then this will just turn into tangent squared plus 1. That's what I missed, rather than going back and doing the whole thing. Okay, 1/3 secant squared theta d theta should be my derivative of that thing. So now I'll factor out the 2 and rewrite my x's. So 2 integral, that's a squiggly integral, 1 over x is 1/3 tangent theta, and instead of my square root, I will tell you what I think about in my head. So this x squared, like we said, is going to multiply with the 1/3 and make 1/9. So I will lose that 9 out front. This is tangent squared plus 1, which is what I wanted, because that's just secant squared. And if I take the square root of that, then this is just secant theta. And then I have times my dx, which is 1/3 secant squared theta d theta. Okay, secant divided by secant, and 1/3 divided by 1/3. So this can be simplified to 2 integral, yikes, it's an ugly 2 and an ugly integral. Oh, not so bad, don't make that much fun of me. Do you ever feel bad for making fun of inanimate objects? Hey, Rock, you look dumb. I don't know, it's kind of rude. What if they actually have feelings? All right, secant over tangent. So this is really, if I break this down as sine and cosine for you, 1 over cosine times cosine over sine d theta. Cosine divided by cosine is gone. 1 over sine is cosecant, so this is 2 integral of cosecant theta d theta. So pretty. All right, and the integrand, which I know we all remember, definitely, 100% definitely, is cosecant plus cotangent plus c, but this is all in theta, and I don't want theta. I want to say that tangent, or tan apparently, is 3x. So let's make my triangular. As done got theta, and tangent is opposite over adjacent. So hey-oh, magically 9x squared plus 1 comes in. All right, now cosecant is related to sine. So hypotenuse over opposite, and adjacent over opposite. So I'll have my opposite in my denominator. So I'm just going to go ahead and write a denominator with a 3x. So this will be negative 2 ln absolute value hypotenuse, so 9x squared plus 1, plus adjacent, which is 1, over opposite, which is 3x. Close my absolute, plus c. Alrighty, that's it for this one. Okay, we got one more. Uno más para ti. Oh, and we have a definite integral. So hopefully this is a little bit nicer, because then I won't have to rewrite it in terms of x again, is my hope, if I can evaluate trig functions. So looking here, I don't have anything nice. There's no identities, especially since this is to the 5/2. Integration by parts is no-go on this one too, since it's a negative exponent. So let's let t be, let's see, I have 1 minus a variable squared. So I will want to do that variable as sine. And it's just a 1, so I don't need to add any coefficient multipliers. So dt is cosine theta d theta. So now here's where you need to pay attention to my bounds. Because if t is root 3 over 2, this is root 3 over 2 when sine is pi over 3. And t is 0, 0, 0 when sine is 0. So I'm going from 0 to pi over 3. And this just allows me to not have to substitute it in back in terms of x. So it saves me a step in there in the end. So this will be 1 over, I'm going to go ahead and write this one out. 1 minus sine squared is cosine squared. So cosine squared, just to kind of remind you guys of fractional exponents, 2 to the 5 halves times cosine theta d theta for my dt. All right, so then I will have cosine to the 5th down there. The 2's will divide out, so I have cosine to the 5th. And then divided by the cosine, and cosine will make that cosine to the 4th. So this is really secant to the 4th. So from 0 to pi over 3, secant to the 4th, theta d theta. What can I do with that? I can rewrite one of the secants. Let's see. As tangent squared plus 1. Because then if I let u equal tangent, then du is secant squared d theta. So now I can rewrite my bounds again. You're so excited. I know you're so excited, but I actually am kind of excited because tangent of 0 is 0. Tangent of pi over 3, opposite over adjacent, is just root 3. And then this just becomes u squared plus 1 du. Yep. And then it becomes much easier. So u cubed over 3 plus u from 0 to root 3. See, and if you left your bounds off, like if you weren't able to evaluate trig functions, then you would have had to go back 2 substitutions back to x, and then throw in your root 3 over 2, and it's just, I don't know, to me it's more annoying to do that. Because you are going to have to evaluate trig functions, so you might as well start practicing. So root 3 over 3 plus root 3 minus, this is all going to be 0 plus 0, so that's all dead. And let's go ahead and practice some simplifying. So this will be 3 root 3 over 3 plus root 3. So this will come out as 2 root 3's, right? Because my 3's will divide out, and then 1 root 3 plus 1 root 3 is just 2. Okay, here are some little things too to be aware of, just reminders from pre-cal, is the fact that cosine squared minus sine squared is equal to cosine of 2 theta. That is a double angle identity from pre-cal. It is also true that 2 cosine squared minus 1 is that, and 1 minus 2 sine squared is that. This first one is the one that you will more commonly see if you need to rewrite it as cosine of 2 theta though. The other thing that is extremely useful is the fact that sine 2 theta is equal to 2 sine theta cosine theta, right? Or I can rewrite this, make it the other way around, right? This is true as well. Either way, makes no difference which way, but these double angle identities are going to be useful through this unit. Hint, hint, wink, wink. Make sure you know that. Okay, other than that, please let me know what questions I can help you with. Hopefully this monkey is makes you happy. Happy. Yay. Happy. I think that turned into 2 speech bubbles. I don't know. All right, well, I'll talk to you guys soon.